Welcome back to the Deep Dive, everyone, and a special welcome to our continuing Science Corner series.
Great to be here.
Yeah, this is where we tackle fascinating topics for all you intellectually curious amateur scientists out there.
Always a good goal.
Today, we're diving into something really fundamental, the Zeeman effect.
Ah, yes.
Yeah.
A cornerstone of atomic physics.
We'll explore what it is, how it was discovered, and maybe touch on some, well, surprising places it pops up today. I hear even NASA's involved.
That's right, some very current applications.
So, our mission for this deep dive is pretty clear. Give you a solid, engaging intro to the Zeeman effect. Spark some curiosity, hopefully.
Let's do it. It all starts back in 1896 with Peter Zeeman.
Okay.
He was really motivated by this lingering question from Maxwell and Faraday. Is there a link between magnetism and light? Faraday had tried, but didn't have the right tools, really.
Right. I remember reading Faraday couldn't detect anything. So what did Zeeman do differently? What was his edge?
Well, technology, partly. He had access to much better equipment, specifically a high-resolving diffraction grating.
Okay, break that down. What is that?
Think of it like a prism, but much, much more powerful. It separates light into its component colors, its spectrum, with incredible precision.
Got it. So super precise rainbow maker.
Essentially, yeah. And he used this to look very closely at the light emitted by elements when they were put inside a strong magnetic field.
And what did he see? Did it work right away?
His first attempt used sodium, the element that gives off that distinct yellow light in street lamps. He saw a slight blurring or broadening of that yellow line when the magnet was on. Interesting, but not quite definitive.
Okay, so a hint of something.
Exactly. But the real breakthrough, the Nobel Prize-winning moment, came when he switched to using cadmium as the light source.
Cadmium? Why cadmium?
It just happened to show the effect much more clearly. With cadmium, he didn't just see blurring. He saw the sharp spectral lines, those unique light fingerprints for each element actually split.
Split. Like one line became two or more.
Precisely. Multiple distinct components. It was undeniable proof that a magnetic field could directly influence how atoms emit light. Imagine seeing that for the first time.
Wow. That must have been incredible. A direct link between magnetism and light finally seen. You mentioned Hendrik Lorentz earlier.
Yes, Lorentz was crucial. His electron theory was quite new then, but it offered the first real theoretical handle on Zeeman's observations.
How so?
Lorentz suggested atoms had these charged particles, electrons, moving around. A magnetic field would naturally push on these moving charges, right?
Makes sense.
And that interaction, he theorized, would change the frequency of the light the electrons emitted. It wasn't the full picture. We needed quantum mechanics for that, but it was a vital first step.
Okay, so we had this landmark discovery. Now let's really define it for everyone listening. What is the Zeeman effect, fundamentally?
At its core, the Zeeman effect is just that. The splitting of a single spectral line into several distinct lines or components when the atom emitting the light is in a static magnetic field.
So the magnet causes the light's fingerprint to kind of fan out.
That's a good way to put it. Instead of one sharp line, you get a little cluster of lines close together.
And what's actually causing that split down at the atomic level?
It's all about the interaction between that external magnetic field and the atom's own magnetic properties. Specifically, the magnetic moment of the electrons.
Magnetic moment.
Yeah, electrons aren't just point charges. They have intrinsic properties that make them behave like tiny magnets. This comes from two things. Their orbital motion around the nucleus.
Like a current loop?
Kind of, yeah. And also their intrinsic spin. The electron itself spins, creating its own magnetic field.
Okay, so the atom has tiny internal magnets from its electrons.
Exactly. And when you put the atom in an external magnetic field, these internal magnetic moments interact with the external field. This interaction slightly changes the energy levels of the electrons.
Changes their energy?
Yes, some energy levels get shifted up a tiny bit, others down a tiny bit, depending on how their magnetic moments align with the external field.
Ah, so the starting and ending points for the electron jumps change slightly.
Precisely. And since the energy difference determines the frequency or color of the emitted light, you now get slightly different frequencies for transitions that would have been identical without the magnetic field. Hence the splitting.
That makes sense. The magnetic field is sort of fine-tuning the energy levels inside the atom. Now, I read about a difference between normal and anomalous Zeeman effects. Sounds a bit confusing.
It is a bit historical, that terminology. You don't see normal Zeeman effect used much in modern papers because it's actually quite rare.
The normal one is rare. Okay.
Yeah. The normal effect is the simpler case, where a spectral line splits into exactly three components. This only happens in atoms where the electron spins kind of cancel each other out perfectly,
Yeah.
so there's no net spin magnetism involved.
So orbital motion magnetism only.
Pretty much, yeah.
Yeah.
The anomalous Zeeman effect is what you usually see. It involves splitting into more than three lines, sometimes many more.
And why was that called anomalous?
Because classical physics, and even the early quantum models before electron spin was discovered, just couldn't explain it. The complex splitting patterns only made sense once you included the magnetic moment coming from the electron's intrinsic spin.
So the anomaly was actually pointing towards a missing piece of physics, the electron spin.
Exactly. It was a major clue. There's also something called the Paschen effect.
Oh, what's that?
That happens when the external magnetic field is really strong. So strong that it overwhelms the atom's internal magnetic interactions, specifically the coupling between the electron's spin and its orbital motion.
What's spin-orbit coupling?
It's how the magnetic field created by the electron's orbit interacts with the electron's own spin magnetism. It's an internal effect. In a very strong external field, this internal coupling gets broken, and the splitting pattern simplifies again, but in a different way than the Zeeman effect.
Okay, so weak field is Zeeman, very strong field is Paschen.
That's the gist. But generally today, scientists just refer to the whole phenomenon of magnetic field splitting as the Zeeman effect.
Yeah.
Understanding it includes these different regimes and the historical normal anomalous cases.
Got it. That clears things up. Let's touch on the theory a bit more, but maybe keep it conceptual. No heavy math.
Sure. The basic idea, as we said, is this interaction energy between the atom's magnetic moment and the external field.
Right.
The size of this interaction, the energy shift, depends on a few key things. One is the strength of the external magnetic field, obviously. Stronger field, bigger effect.
Makes sense.
Another is the atom's total magnetic moment. This involves combining the orbital and spin contributions in a, well, quantum mechanical way. We talk about the total electronic angular momentum.
Okay.
And then there are factors like the Bohr magneton. Think of it as the fundamental unit of magnetic moment for an electron, and something called the Landé G factor.
Landé G factor.
Yeah, it's basically a correction factor, a number that tells you how strongly a particular atomic state's magnetic moment actually interacts with the field. It accounts for the complex interplay of spin and orbital angular momentum.
So the splitting isn't always the same. It depends on the specific atom and electron state through this G factor.
Exactly. The energy shift, and therefore the amount of splitting you see, is proportional to the field strength, the Bohr magneton, and this Landé G factor, plus another quantum number related to orientation.
Okay, so field strength and the atom's specific quantum state dictate the split.
That's the core idea. And as we mentioned, the distinction between the Zeeman and Paschen regimes hinges on whether that external field is weak or strong compared to the internal spin-orbit interaction energy.
Right, whether the external magnet bossly takes over or just nudges things.
A good analogy, yes.
Okay, I think we have a decent conceptual grasp now. Let's move to the really exciting part. Where is this effect actually used? What are the applications?
Oh, they are incredibly wide-ranging. A huge one is astrophysics. It started very early on, actually.
Oh, early.
Early 20th century. George Ellery Hale. He used the Zeeman effect by looking at the light from sunspots.
Sunspots.
Yes, and he saw the spectral lines splitting. That was the first direct proof that the sun has strong magnetic fields, especially concentrated in sunspots.
Wow. So it confirmed magnetism on the sun. Why is that so important?
Well, solar magnetic fields are the engine behind almost all solar activity flares, coronal mass ejections, the solar wind. Understanding them is crucial for predicting space weather, which can affect satellites, power grids, even astronauts.
So Zeeman effect helps us predict space weather.
Indirectly, yes. By allowing us to map the sun's magnetic field. Today, astronomers create detailed magnetograms of the sun using this effect, and they also use it to measure magnetic fields on other stars. It's a fundamental tool.
Amazing. From a lab discovery to mapping stars. What else?
Closer to home, in atomic physics labs, it's indispensable for laser cooling.
Cooling atoms with lasers.
Yes, down to incredibly low temperatures, fractions of a degree above absolute zero. Techniques like magneto-optical traps, or MOTs, and Zeeman slowers rely heavily on using magnetic fields to manipulate atomic energy levels, the Zeeman effect, to help slow atoms down with laser light.
Which is key for things like quantum computing research.
Absolutely. And precision measurements, fundamental physics tests, it also underpins aspects of spintronics.
Spintronics, using electron spin for electronics.
Exactly. Controlling electron spins in materials like quantum dots often involves using magnetic fields, and understanding the Zeeman splitting is part of that.
Oh, cool. Okay, astrophysics, laser cooling, spintronics, any more?
Oh, yes. Metrology, the science of measurement. The Zeeman effect can be used to fine-tune atomic clocks.
The most accurate clocks we have?
The very same. Minute adjustments based on Zeeman splitting can help push their accuracy even further. It also has potential in analytical chemistry, maybe improving techniques like atomic absorption spectroscopy.
Measuring tiny amounts of elements.
All right, and then there's a really fascinating, maybe surprising one, biology.
Biology. How does the Zeeman effect show up in biology?
There's a leading theory about how some birds navigate using Earth's magnetic field.
The magnetic sense, I've heard about that.
Well, one hypothesis involves a protein in the bird's retina called cryptochrome. The idea is that incoming light creates pairs of radical molecules within this protein, and the quantum spin states of these radicals are sensitive to the direction of the Earth's magnetic field, possibly via a mechanism related to Zeeman interactions.
Wait, so birds might be using quantum mechanics and the Zeeman effect to find their way?
It's still an active area of research, but yes, that's the gist of the theory. It suggests a quantum compass sensitive to tiny magnetic fields. It's pretty mind-blowing, if true.
That really is a natural quantum device.
It-
Amazing.
And we shouldn't forget the nuclear version, the nuclear Zeeman effect.
Nuclei have magnetic moments too.
They do, much weaker than electrons, but measurable. The splitting of nuclear energy levels in a magnetic field is the fundamental principle behind NMR, nuclear magnetic resonance spectroscopy.
Which chemists use all the time to figure out molecular structures.
Exactly, and also MRI, magnetic resonance imaging in medicine.
Of course. MRI uses huge magnets.
Precisely. It's probing the nuclear Zeeman effect in the protons of water molecules in your body. There's also Nussbauer spectroscopy, another important technique in physics and chemistry that relies on it.
Okay, so NMR, MRI, Nussbauer,
Yeah.
all based on the nuclear version of this effect. The reach is just incredible. Now, you mentioned NASA at the start. How are they using this?
Right, this brings us right up to the present day. NASA launched a mission called EZE, that's EZIE, the Electrojet Zeeman Imaging Explorer.
Electrojet Zeeman Imaging Explorer. Okay. When was this?
Launched quite recently, in March 2025. It's a heliophysics mission focused on studying Earth's upper atmosphere.
Heliophysics studying the sun's influence on Earth.
Correct. Specifically, EZIE is looking at the auroral electrojets. These are intense electric currents flowing way up in the ionosphere linked to the aurora. They're a key part of space weather.
And Zeeman is in the name, so.
You got it. EZIE is designed to study these electrojets by observing Zeeman splitting.
How? What's splitting up there?
The mission uses 3 small satellites, CubeSats actually, to look at microwave emissions from oxygen molecules in the upper atmosphere, specifically in the mission line around 118 gigahertz.
Okay.
And one of the instruments, called MEM, the microwave electrojet magnetogram, just recently achieved a major first. It successfully measured the Zeeman splitting of that oxygen line in the ionosphere, directly caused by the magnetic fields associated with the electrojets.
Oh, wow. So they're using the exact principle Zeeman discovered in 1896, but applying it remotely from space to measure currents high above Earth.
That's exactly it. By measuring how much that oxygen line splits, they can infer the strength and structure of the magnetic fields generated by the electrojets. This gives us completely new insights into how these currents behave and how they connect to space weather phenomena.
That is just fantastic. It perfectly connects the fundamental lab science to cutting-edge space exploration.
It really does. It shows how powerful these fundamental discoveries are. Their relevance just keeps unfolding in new ways.
This has been incredibly enlightening. Let's try and wrap this up. We've journeyed from Peter Zeeman's initial discovery in 1896
Seeing those spectral lines split in a magnetic field,
to understanding the cause, that interaction between the external field and the electron's own magnetic properties, its orbital motion and spin shifting energy levels.
which leads to the splitting of the light emitted or absorbed.
We touched on the historical normal versus anomalous distinction and how the anomalous was actually the common case, pointing towards electron spin.
And the Paschen back effect in very strong fields.
And then the applications. Just, wow, from decoding the sun's and stars' magnetic fields
Essential for astrophysics and space weather.
to enabling ultra-cold atom experiments and potentially spintronics.
Plus refining atomic clocks, maybe even bird navigation.
That bird navigation part is still wild to think about.
It is. And of course, the nuclear Zeeman effect underpinning NMR and MRI.
And capping it off with NASA's EASY mission, using Zeeman splitting of oxygen lines to study Earth's own electrojets from space.
Yeah, it's a testament to how a seemingly subtle effect provides this incredibly versatile tool for probing magnetic fields everywhere, from atoms to stars to our own planet's atmosphere.
It really makes you stop and think how a careful observation in a lab over a century ago keeps finding new and vital roles in 21st century science. What other fundamental principles are out there, maybe things we already know but haven't fully exploited, that could unlock future breakthroughs?
That's always the exciting question in science.
Indeed. Something for you, our listeners, to ponder. Maybe dive deeper into EZE or look into cryptochromes and bird navigation. The rabbit hole goes deep. Thank you so much for joining us for this fascinating deep dive.
My pleasure.